So yeah, my talk today is about fuel cell vehicles and where they are today. So the last talk given here on fuel cell vehicles was by Keith Whipke a couple of years ago. It was just before the Mirai was coming out, and the other vehicles were coming out onto the market. And he titled it Fuel Cell Vehicles for the Future, and so I changed it to where they are today, so that there's more of an emphasis on what's actually happening right now. I've been managing the fuel cell vehicle program here, where we have 3 fuel cell vehicles on campus right now that NREL employees can check out and drive to events and things like that, and just get an idea of how they work. And doing these events, I get lots of questions. So I was trying to get those questions answered here, and I was going to use those questions as the basis for this talk. So that's kind of my idea, and feel free to ask questions throughout as you'd like. So these are the 3 fuel cell vehicles on the market right now. The Toyota Mirai has been on the market for about a year. I just looked at its sales numbers this morning. They're selling about 40 a month for the first year, but then a couple of months ago they had a month where they sold 370. So there's quite a bit in California right now. They're only available in California. That's where the fueling infrastructure is. The Hyundai Tucson is let's see, that's the white one here. That one has been around a bit more. It's only available for lease. I don't know those numbers offhand. Then the Honda Clarity has gone for sale in Japan right now. It hasn't come to the US yet, but they're planning on it soon. I don't know if it's going to be by the end of the year or early next year, but that's their plan for the Clarity. I took the spec sheets from the Toyota Mirai and compiled some of the specs that most people want to hear about it when I go to these events. So the torque is 147 foot-pounds. The storage, you can store 70 megapascals of pressure on there, which is about 10,000 psi. There's 5 kilograms of hydrogen on board, and fueling time takes about 5 minutes. And as we found, that's a pretty conservative estimate. We can get down to 3 or 4 minutes usually with our fueling station out back. The vehicle can go 312 miles on a fill, and that depends on driving conditions, of course, and the driver. If you accelerate a lot faster, then your range will go down. There's actually a power mode and an eco mode on the Mirai, so you can put it in eco mode, and you definitely don't have the pickup, but you can conserve your miles. If you put it in power mode, you can go a lot faster. Its acceleration is 0 to 60 in 9 seconds, which isn't too bad. Its curb weight is a bit heavier than a conventional vehicle. I'm not sure exactly where the weight comes from, but that's one question I haven't been able to answer yet.
Does it have a storage battery? The fuel cell does electricity, and then the storage battery delivered to the wheels as needed?
Yes, it has the equivalent of a hybrid battery on board, so it can store
kilowatt hours or 2 kilowatt hours.
Yeah, so it can store the regenerative braking, and when you let off the accelerator, there's still hydrogen going through the fuel cell that it can divert to the battery rather than to the wheels.
So the hydrogen runs a generator, and then the generator?
No, it runs directly off the hydrogen fuel cell. So the battery can assist as it needs to, but its main source of power is from the fuel cell.
So the battery's just buffering?
Yeah, exactly. So it can give some initial get up and then store on your braking as well. So.
Are
Yes.
These PAM membrane fuel cells we're talking about?
They are. Those are the lightest and most suitable for transportation right now. So yeah, the pricing that's out right now, they just it's 57.5 for to buy, and the leases they just dropped it to $349 a month. It was $499, and they just announced last month that it's going down to $349. All fuel and maintenance is included, and I'll get into reasons for fuel being included later on here. So. There's also fuel cell buses that are being run right now. I do a lot of work with the fuel cell bus analysis here. So there's in AC Transit, there's 13 fuel cell buses being run in their fleet right now. It's a demonstration project that's been going on for 5 years now, I think. And the next biggest is Sunline. They actually have 2 different projects going on there, but 4 buses in total at their depot, and the rest are a couple buses here and there. So the buses have been demonstrated to run really well. The drivers seem to like them. They're really quiet compared to diesel buses. They only put out water from the tailpipe, so people really like it. There's actually a complaint on the buses when the air conditioner would kick on. The noise from the air conditioner was so loud, but it's the same air conditioner as regular buses. They just didn't have the engine noise to cover it up, so that intermittent sound from them became a source of complaint once you took away the engine noise.
What's the hydrogen pressure on the buses?
Those are half the pressure. They're 5,000 psi. Because you got so much room, you can do bigger tanks on them and not have your loss that way. So these are a couple that are slated for the future. This one is an actual going to be a production vehicle coming early 2017, and this is a concept vehicle for Lexus. It's kind of has some interesting stylings that'll be toned down as they go to their production version. All right, so I get the question a lot of how does a fuel cell vehicle work? You open the hood, and you don't see too much under the hood because it's all the power control unit and the motors underneath there, and it's got an air intake and your auxiliary components. That it's not really what actually runs the car. So people always ask to point out what does everything, and I have to show them the diagram of where everything is in the vehicle. So to start out, we've got the fueling tanks. There's 2 of them in the vehicle. There's a bigger one under the back seat and a smaller one just in the back, in the front of the trunk there. So those will supply. You can kind of see. Here's the line right here. So it sends the hydrogen to the fuel cell stack, which is underneath the driver's and passenger seat. So that. Then also what they're missing on here, that there's an air compressor up here that sends air to the fuel cell stack as well. So you supply the oxygen from the air and hydrogen to create electricity and goes through a boost converter, which basically conditions the power. Yes?
How serious is air filtration? Like on ICE, you have the air filter that you got to change. Is this very similar to that?
Yeah. So you don't want to introduce too many impurities. There's a lot of studies going on. There's a fuel cell test beds over here on our at NREL, and so they can supply different impurities to the fuel cell on both the cathode and anode side, so they can see which impurity is affected as as time goes on. And so yeah, they'll take different impurities that would come from a vehicle in front of you, say, and see how that would affect the fuel cell. But right now there hasn't been too much degradation just from the air side of the fuel cell, as far as I know at least.
And this is a rear wheel drive, I'm assuming, right?
I think it's front wheel. Yeah, it's front wheel drive.
Oh.
Now, how about the water coming off the fuel cell? Is there a small drip line on the exhaust?
Yeah, you can-
Called exhaust?
You can see water dripping out. I was going to get into that a bit later, so
Okay.
yes.
Those hydrogen tanks there, what protection do you have in case of collision?
In case of collision, the tanks themselves are reinforced quite a bit. They're made of carbon fiber, so they're wound with carbon fiber. So the tanks are really strong, and I actually have a picture later on of a in my safety section here where it was a compressed natural gas vehicle that was rear-ended with that had a storage tank, and it's similar to the hydrogen ones. Just the hydrogen ones are a bit thicker because they're higher pressure, but the tank actually stopped the impact from reaching the driver, so it actually added safety to the vehicle.
You know, I was thinking in terms of something really major, like a collision inside a tunnel, like the Grand San Bernard, Switzerland, or something like that. You know, they had that fire that they couldn't even get out of for 3 days.
Yeah,
The Grand San Bernard tunnel.
yeah. I'll get into that a bit later. And I've got some parts of the I've got some safety comments in there as well. So thanks though. I'll let you know later on there. So basically you've got your hybrid battery back here as well, and then so the fuel cell and the hybrid battery can supply to the motor here and drive the car. And then people ask, how does a fuel cell work? I'm a chemist, but don't know exactly all the little details of a fuel cell. I work more on the infrastructure side right now, but I can, if you have questions about exact catalysts and everything, I can direct you to people that do that every day. But in general, it's a pretty simple process. You put hydrogen in on one side, and you put air on the other side. You can just recirculate the hydrogen through to keep a fresh supply going against the membrane, and the oxygen, the hydrogen will permeate through the membrane, and as it does that, the electrons get stripped off of it through the membrane. It's an interesting membrane. It has to permeate hydrogen through, but also conduct electricity. So you can capture the electricity through the membrane and bring it back around through your system and come back around to supply the electrons back on the other side. So you basically are taking the oxygen and reacting it with the hydrogen through the membrane to create electricity and then just make water. So here's a demonstration project we did last week where we took two of the fuel cell vehicles we have up to the Continental Divide. So we wanted to demonstrate the fueling capability that we have here, and also show that the vehicles can be used and show the range of the vehicles basically. So we took them up to up I-70 up to Breckenridge and came back down 285 through Fairplay. And so we did a loop that was more than 175 miles. We fueled the vehicles before and after, and just to show that you can bring it in and fuel it just like a gasoline vehicle would be today. So getting into stations, I took this from the alternative fueling station locator, which any fueling station can add in their kinds of fueling stations to this locator, and you can go through and find, if you have a CNG vehicle, you can go to the next station. The hydrogen definitely has the fewest number on the database. Currently, there's 29 stations. 26 of them are in California. So that's why all the manufacturers are starting out in California. There's a few on the East Coast here that are starting up. But they're really ramping up the production of the stations. So in the next year, they're supposed to be, these are all permitted and ready to go in some stage of completion. So the next year, they'll come close to doubling the amount of stations, and that'll hopefully allow more vehicles on the road and sustain the vehicles that are going right now.
So are these stations being loaded out of a big tank truck, or are they using power to do the hydrogen generation?
That's a good question, actually. Let's see. Yeah, later on I kind of go through how some stations are done, but they kind of have a mix right now because they don't know what the best option is. So there's some that do on-site electrolysis, some that do on-site steam methane reforming, some that have delivery, some deliver a big set of tanks that you can put a new one on and pull the old one off, and some deliver liquid hydrogen. So they're going through the options right now and trying to settle in what the best option is. So seeing that there's so few stations, it kind of leads you to think, when is this actually going to start ramping up? And so you get headlines like this where weak hydrogen infrastructure delays Toyota Mirai sales, and Toyota tells dealers stop Mirai deliveries. So that it's kind of there's kind of some pushback from the dealers. They want to get these vehicles out, and there's not the stations out there. So there's kind of a balance going on right now of where's the hydrogen coming from to supply the vehicles, and the vehicles are ready to go. So this comes up to what NREL is working on with infrastructure challenges. So
Tesla got ahead of this on electric by starting superchargers
yeah,
across the country.
yeah,
Toyota didn't go and do a similar thing.
right. Toyota is actually funding some stations now, so they're kind of going that route as well. So they're doing a lot of the East Coast ones and supplementing some in the California side. So yeah, funding is not my main point of expertise. But I can find you more information on that if you're interested. So there's a few things that need to happen for the stations to become really prevalent. So the reliability is a big thing that we're working on here. We have a test station out back of the ESIF where we have different size compressors that we can, in a big pad where we can swap in components and try out different chillers and everything. And we can actually we have one dispenser here. We have space if we want to put a second one there and test out 2 different dispensers. So there's a lot we can do, and we're really working on ramping that up. But a couple of the main components that fail are the compressor, and that leads to downtime. And what the manufacturers don't want is someone coming up to a station and having it be shut down because of maintenance, and have that kind of be the stigma attached with it. So they really want that to be worked out. A lot of people say, oh, that's just engineering, but that engineering needs to be done still, and that's what we're working on. The next, another.
So are you saying
yes.
That's an issue that pops up?
Yeah, people come up to stations and they're down for maintenance, or or something. The database that I showed earlier, you can go on and see if it's offline, and sometimes it's accurate, and sometimes you'll get there and there won't be the supply or something, and so.
So are these really hard problems to solve then? I mean, these mechanical issues?
That's what we're working on figuring out now, is how we can improve the reliability of everything. So we actually just got a project awarded where we're going to be testing out different components. We'll get 40 valves that have been found to be leaking readily out back, and run them continuously at different conditions, and see what we can do with, and then take them apart and dissect them, see where the problems lie, and say, hey, this material is too soft or too hard or something, and we can start working with manufacturers. That's a big key part of it, is working with the manufacturers to say, hey, this is what needs to happen, and we hope to get those reliability issues down quite a bit.
So is the main issue volatility then?
There's a few different issues. There's a big one with, because it's such high pressure, and then also to fill the vehicles, you have to pre-cool to get to the time down. So, because as you compress gas, it heats, so you want to start at a low temperature. So you got high pressure and low temperature, and seals really don't like that combination. So sealing surfaces is kind of a big issue there. And then compressors, it's kind of the same sealing issue, is where you have a big piston compressing the gas. It has to slide against some component, and that wears down. And they have rebuild kits, and they find that you have to rebuild it more often than other gases because it's a small molecule that can escape. And there's also embrittlement issues that different materials can be embrittled by hydrogen. So there's been one of the failures at one of the stations, actually at AC Transit, the bus company. There was a valve that was selected incorrectly. It was a relief valve, and the inner component was found to have shattered and relieved all the gas, and that was it was right next door to Pixar Studios, and they had to evacuate. The fire department came in and evacuated this 2-mile radius, which included Pixar Studios. So it was a big mess right then, and they were down for 5 or 6 months while they were trying to, come back and say, hey, this is actually safe. When the engineers got on site, they said, oh, this is a non-issue. It vented properly, did everything that it was supposed to do. But there's a lot of public awareness that has to be done as well. So, and working with the fire departments is a big point as well. That's what they really wanted to do with that downtime, is work with the fire department, come up with a plan to say, hey, this is what you need to do in this situation, and try to keep them from evacuating the area if they don't need to. And so.
I would imagine the frequency of problems in the mechanical area are a function of that high pressure.
Yeah.
What are the difference between maintenance problems at the 5,000 PSI level to the 10,000 PSI level? An order of magnitude or something.
Yeah, because with the 5,000, it's found that you don't really need to pre-cool.
Yes.
And so you can compress the tanks, and they stay at a low enough temperature that you don't have to pre-cool, so you eliminate your temperature issues. So yeah, it's really quite a bit. They're really quite less. That's why they use it on the buses. But yeah, the auto manufacturers have gotten together and kind of said, hey, this is the pressure we need to keep it down to a size that we can keep on a vehicle. Because the tanks are pretty big, and they're a cylinder, which is not the easiest shape to work around on a vehicle, but it's the strongest shape to use on to contain the gas. So yeah, there's kind of been some back and forth. Honda's wanted to keep it lower for a while, and then they kind of started doing the high pressure as well. They're working on, they kept saying, let's keep it at 35 MPa, which is 5,000 PSI. And then I said, well, let's go to 50 MPa, which is 7,000 PSI or so. But all the other auto manufacturers said, no, we want to do 10,000 PSI, and we just need people to engineer around that. And so that that's kind of where the 10,000 PSI came from.
So that's all to get range? That's for the volume and the given, or the mass in a given volume?
Exactly.
Range, so they can advertise range.
Exactly.
Of course, there's a big energy penalty in compressing up to 10,000 PSI.
Exactly. Yep.
So is it fair to summarize, the cars seem to be fine, it's the charging structure that's still needing to mature?
That's kind of what where we're going right now with there's definitely more projects being done with infrastructure reliability, and the auto manufacturers have taken care of everything else on their end. So they've been building up their vehicles and thinking that the infrastructure would build up along with them, but they're starting to find that didn't happen. So yeah, that's leading Toyota to do a lot more work with that now. So
what is the situation in Japan?
In Japan, it's pretty similar. Japan has some different pressure safety factors. So everything they do, it has a lot thicker walls, like a lot thicker of a tubing wall and everything. So they've got a bit. So everything they do is a lot more expensive because of that requirement. So that's one downside to the safety factor. But yeah, they have a lot of the same issues though, and they've got some of their projects going on as well. So in fact, the meter accuracy is a big one going on right now because the meters haven't been as accurate as they need to be for selling the fuel. So that's why the fuel is included with the sales price. So that's how they got around it to start selling the vehicles. So but they're hoping to get that down here. We actually have a project here where we're benchmarking flow meters, and we just had a Japanese manufacturer in a couple weeks ago that we're working with to benchmark their meter, and so they gave us the meter to work with, and we're giving them the data on the meter. So we're really hoping to work with other manufacturers as well, and really get that metering down. So.
Aside from the fire department, what are the permitting?
So talking to the AHJ, the authority having jurisdiction, he can sign off on whatever he wants, really. So California's kind of gotten a system down. They started kind of piecemeal where they it's a new technology, so the AHJ would have to sign off on different components, whereas when they sign off on some building permit, they sign off on the electrical and then the structure. Or on other fueling stations, they can just sign off this fueling station meets everything. But they've kind of piecemealed it in the beginning, and now they've got it all together where they can sign off on the station as a whole. Colorado just actually adopted that model, so they can start off the bat and just permit a station as one entity. Where so that's kind of forward thinking on Colorado right now, but it's all state by state, and it's all done differently at every state. So that makes it kind of a challenge, trying to get everything standardized, and one state might require one thing where another state won't. So that's the big challenge with the station permitting right now. So this is our test pad out back. It's really spread out compared to what you would see at a regular fueling station. We've got a lot of room here where you can add extra components and try out other things. So this is the high pressure compressor. So basically it starts out here. You can see this little track right here. That's an underground trench. We have an electrolyzer inside that sends hydrogen out to the low pressure storage tanks. Then those get boosted up by the medium pressure to the medium pressure storage tanks, and then the high pressure to the high pressure tanks.
So what are the PSI for low, medium, and high here?
The low is a couple hundred PSI. I think it comes from the compressor, or from the electrolyzer at, I forget exactly, I want to say 200 PSI. And then it'll boost to the medium storage, which is around 6,000 PSI, and then to the high storage, which is 12,005 or 13,000 PSI. So, yes?
Just curious, why have 3 different pressure levels in the storage?
So the electrolyzer can, and that's actually a good point. A lot of stations now going to a single stage where they'll boost it all at once, and some of those the compressors can do that now. This was kind of the standard a couple of years ago when they would boost to medium pressure and then go to a high pressure storage. So they would do what was called cascade filling. So you can the medium pressure bank doesn't take as much of a pressure loss because you don't have to compress it all the way up. So you can start a half fill with your low pressure banks and not have to use that pressure from the high pressure banks.
Well, just to continue then, what pressure do you use to dispense it, or will they use to dispense the hydrogen to the filling stations?
So if they do the cascade fills, they can start with the lower pressure tanks, and wherever the vehicle is, they can boost it up to a little below that, and then they can switch over to the higher pressure banks.
The station will actually have three different pressures?
Yep, it might, and that's still being tested out, which method is the best. If they'll do a cascade fill like that, or if they'll do direct compression into a vehicle, or there's a lot of different methods that people are trying.
Well, if I were in a community that was whether they were applying for permits, my concern would be something on the order of what happened in San Bruno a few years ago, where an entire neighborhood was completely devastated by a gas leak. What happens if you get in a place like California, for instance, where you're subject to earthquakes? Yeah, you get a ruptured hydrogen line below ground.
Well, that's a good point. So I'm not sure what gas was leaked there. Was it a methane leak or?
You're going to have 3 lines. Look, what you're telling me, you're going to have 3 different lines running at 3 different pressures.
Mm-hmm.
If you rupture a high pressure line, you might flatten the whole neighborhood.
Well, the lines they have a flow restrictor, so it won't be able to flow fast enough, and also if it's flowing fast enough to be faster than what you would fill a vehicle with, it has shut-off valves that would.
What you're saying then is if the flow rate suddenly goes through a major change upward, it will shut down automatically?
Yeah, and so there's a shutdown there, and then also hydrogen. It's really buoyant. It'll float. It'll go really fast, and so it won't go too far around. It'll go straight up. So it's going to go away really quickly. So,
Still, you know, just with these type of considerations, most of us, and I'd have to include myself, don't have a good enough understanding of it. For instance, if I were the one to issue a permit, somebody would have to do a very good job of selling me on the thing was adequately
Yep.
adequate safety precautions.
yep, and
I think that's going to be a hard job.
yep.
So Carl, we're gonna get over here. to that.
I've done that job.
You
resemble that
that.
I initiated the project to create a national code for hydrogen safety, and that, I'm very happy to say that that project has reached fruition. We do have now a national.
You know, if I'm, say, at a county level, say, when I'm going to issue the permit,
Yeah.
somebody's going to have to rub my nose good hard in that, in the fact that it's going to be safe.
Well, the code is loaded with good stuff. I mean, it really is very comprehensive, and
Well,
it is now become really a national code.
A national code.
Yeah, and it's used throughout the United
So
States.
most, if not all places would adopt that code, would use that. In effect, the supplier would abide by that code.
Yes, as a matter of fact, Colorado, which is about to adopt regulations that would allow the building permitting of hydrogen fueling stations, has through reference adopted this NFPA hydrogen code.
Is there any cooling in this?
The cooling is, the dispenser is off on this side, and the cooling is done at the dispenser. So the chiller is back here. I think I've got a picture of it later on here. So one other, so I'm getting into more of NREL's testing here. So this is the hose reliability study. So the hoses, you take them off and move them around it, and so that they get used quite a bit, and they need to be replaced periodically. So this is actually a robot that was built here, or it's a robot that is used here to simulate that testing or that movement, and really put the hose under its paces. So it'll connect to one receptacle, pressurize up, and depressurize, come up, and then it goes to one off to the side. So it kind of simulates a couple different spots where a car could park. And they do inspections before and after, and it's in a high pressure test bay out back, so they can test it to failure if they want to go that far. They can monitor if it starts losing pressure, and there's monitoring in there in case there's a leak detected. And
What is the temperature going through the hose and when pressurizing for a 10K automobile?
yeah, so this one, they've got a chiller here, so it simulates the chilling as well. So they can flow the low temperature gas through it as well. So, and then let it heat up again.
Well, what temperature is it?
It's negative 40.
Negative
for it.
40 C.
Yep. Well, C and F. That's the point they meet.
Right.
Again, you've got glass safe and nozzle and other components to replace as needed. Is there any code requirement that they should be replaced at a certain number of hours?
There is.
Because it's like on an aircraft. You don't wait till an engine breaks down in flight. You replace it after whatever, 5,000 hours or whatever.
Yeah, so it's number of fills is what it's based on, and I don't know that number offhand. But I know there is a requirement to replace them after a certain number of fills. So then this is the H2 First project that has been started here. It's a partnership between Sandia and NREL. So it's kind of a group that determines what projects needs to be done, and so they've kind of worked with the DOE to fund different projects at the national labs. So one of those projects is the HighStep Device. So this is a device that's on a trailer they can bring to fueling stations and check if it's meeting the flow accuracies, the flow rates, if it's meeting the temperatures and quality of the gas. So it used to be that each OEM would have to certify the station themselves, and they would bring their vehicle tester there and test for a week, and then the next one would come, and they'd want to do it twice, and so it'd basically take 6 weeks for a station to be accepted. But with the HighStep device, they can bring this trailer there, and all the OEMs agreed to accept that as a certification and go from there. This is the gravimetric standard, so this is what we're testing the flow meters on right now. We have a high accuracy scale that's actually not in the picture yet. I should have taken a new picture for this, but so we have a scale that can weigh the hydrogen that's being flown through the flow meter, and so we can get a gravimetric measurement of what's been through the flow meter and then compare it to what the flow meter's output is. So we're getting some really good data from this. We can control the control nozzle before and after, or the control valve before and after the flow meter, so we can see how it performs at constant high pressure, or if it can work the same way through the whole range of pressures through a fill. This is the video that Carl has been working on. So this is a permitting video that it goes through all the steps needed to permit a station. So it just came out last week, right, Carl? So this is going to be a big help for people trying to put stations online. So the next question I get is, where does the hydrogen come from? So there's 2 methods right now that are being used. There's some other methods that are being looked at, making the hydrogen from algae or other catalysts. But the 2 main ones used right now are steam methane reforming, which is what is mainly producing the hydrogen right now for all of NASA's use and everything like that, and other oil-related uses. And then electrolysis is basically splitting water. It's doing the opposite reaction as a fuel cell does, where you put in electricity and you split water and hydrogen out. So the steam methane reforming, it's the cheapest method right now, and there's a lot of methane out there to use. But it does make CO2, and it's a fossil-based gas. So the electrolysis it's more expensive, but it can be done with renewable sources. You can use wind and solar to provide the electricity to split the water.
So when you say cheapest and more expensive, what price, assuming that electricity rates stay where they're at, because renewables are coming down, but the gas can fluctuate dramatically
Right.
on price, where would the crossover, how many dollars per million does it become washed?
That's the $1 million question right now. I don't have that answer, and there's a lot of people trying to come up with that answer, and so I don't know right now. I can ask some people and see if I can find that answer for you.
Do you have some snapshot price comparison today?
Let's see. So right now I think the initial price would be about $8 per kilogram. So a kilogram is about, so there's 5 kilograms on the Mirai, so that would be about a $40 fill. So when gasoline was getting to be about $6 some per gallon, that was when it was about equal, and then gasoline came down and again. So.
And the $8 is for SMR production, right? Or not necessarily?
I would think so right now. But don't quote me on that. That's what I've what I've heard. I'm not 100% sure on that number.
Let me clarify my question, because there's a few different price comparisons.
Exactly.
I was trying to ask, between the two, what is the natural gas level that brings
Gotcha.
it, so it's no longer, brings the SMR up on a cost basis to the electrolysis,
Gotcha.
assuming a fixed electrical
Yeah,
cost?
I don't have that number.
Okay.
Yeah, I'd have to ask some of our modeling people what they think of that. And
Yeah, okay.
Are there kind of large-scale electrolysis sites now?
yeah, our electrolyzer back in the lab, it's probably that tall, but it'll be able to fill 5 cars a day with just that stack, and then you can scale them up. And
So you just feed it with electricity and water?
yep,
And
and if you want to do more, you just stack them higher. So yeah, there's definitely capacity to go there. So to build up a fueling station, once you get it there, you'll start with a smaller electrolyzer, and then once you want to accommodate more cars, you can build to that stack. And so you can start out lower to accommodate what's on the market now and build up the same station if you needed to.
so it takes a significant amount of electricity?
It does. So I forget the exact losses. It's probably a 30% hit there, and then so yeah, you don't get nearly as much joules of hydrogen out as you put in, but it's a way to store energy basically. Then there's 2 different ways to get the hydrogen to a fueling station. You can produce it on site, or you can have it delivered. They're both being tested, like I said earlier. So I won't work on that too much. This didn't come across all the way. So this slide is supposed to be about our NFC Tech, the National Fuel Cell Technology Evaluation Center. So
If you click through, I think it's a sequential.
oh, it is. Okay. I didn't realize it did that. I just copied and pasted from a different slide. So basically we collect data from manufacturers, and we try to get a good idea of where the market is today, so that we can work with the manufacturers and send them back data products that show their numbers versus what's on the market today. And then out to the public, we just send out composite data products, so they can't identify one manufacturer to another, but still get an idea of where the whole market is. And then another big project that's just starting is called H2 at scale. So it's basically taking the energy systems at the ESIF and combining the hydrogen into that. So how do we take the existing infrastructure and work in hydrogen and come out with the best products around? So this is just coming out. I don't know all the details on this. So I can. I just know this graphic. It shows quite a bit here, where you have renewables coming onto the grid, and then making the hydrogen, and you can use it in different vehicles and everything, and then come back on the grid if you need to. It's an exciting new project going on. So here's where I talk about the water coming out of the vehicles. So a lot of people always ask about the water, because you can see it coming out there. That's what it looks like when you park. So people say is that bad? And because So basically you have your, compared to gasoline, you have a certain number you have 284 kilojoules coming out per hydrogen atom and 121 per hydrogen atom in a fuel cell reaction. So that makes about 2.35 times as much water from the same power of gasoline as hydrogen. But fuel cells are about twice as efficient as a gasoline engine, so that brings it down to be pretty similar level of water coming out from gasoline versus hydrogen. The main difference is the water coming out of a fuel cell is a lot lower temperature, so you can see that coming out as water, whereas in a gasoline internal combustion engine, it comes out as water vapor, and you don't even see it usually unless it's cold out. You can see it start to condense. Then people have asked as well, isn't water vapor the highest contributor to greenhouse gases? Which is definitely true, but the water comes out after a few days of whenever you get the clouds coming out and it starts raining. That precipitates out, and its cycle is really low-lived. Where if you get carbon dioxide, that's lifetime is a long time in the air, so it's hard to get back out. And then also the little increase in temperature from carbon dioxide also increases the amount of water that can stay in the air. So that is kind of a double hit there. So let's see. So basically, and then another point is the water coming from gasoline is coming from hydrogen that's stored as gasoline as a fossil fuel underground, and then you're releasing it back as water, whereas the water from fuel cells starts out as water and then ends back as water. So. And then we're coming to the is it safe question that people always come up with. So 1 kilogram of gasoline is about equivalent to 1 gallon of gasoline, or one gallon of gasoline is 1 kilogram of hydrogen. So the Mirai store is 5 kilograms, whereas the Camry store is 17 gallons of gasoline. So you have a lot less energy stored on board, actually, in the form of combustible fuel. Yes?
Would you say, one of those slides further back, it said that the efficiency was 30 to 40%, was that right?
Of a fuel?
The efficiency of the vehicle in terms of all the energy input it took to get to that hydrogen to the vehicle, plus what, in other words, the vehicle's giving you a certain amount of power, and a certain amount of this had to be a certain amount of power input to get the hydrogen to the vehicle, make it get it there.
Right. So, yeah. So there's a
30, 40%, what you said.
So you're talking about the electricity from the beginning. So there's probably a 30% hit.
All the total input, the energy input to generate the hydrogen, and then what you're actually getting out in the car.
Yep. So the electricity coming in, you take about a 30% hit to create the hydrogen, and then another 30% hit to get it back out. So you're looking at about half the efficiency of.
In terms then of waste heat in the vehicle, it would be considerably less than any combustion engine.
Exactly. That's why water comes out as liquid water quite a bit versus water vapor. So there's a lot less waste heat.
With that system, of course, depending on how you generate the electricity in the first place, but all you're doing is borrowing water for a while, then returning it.
Exactly. That's the idea. So,
It
yeah.
doesn't solve the drought problem in Alaska.
No. That brings up another observation is without the waste heat of an internal combustion engine that uses that waste heat to heat the cabin and everything. You have to use electric heaters in a fuel cell, and the same as an electric vehicle. So you have a lot less efficiency if you're using the heater and auxiliary things as well. But fuel cell vehicles are working a lot with the knowledge from electric vehicles that are out there today. So that's really getting, there's a lot of solutions out there right now for that. So here's one of the gas cylinders from the Mirai. It's got a cutout here, so you can see the end boss here. This, if there's a line cut and it can detect if it's flowing too fast, and it'll shut the valve in here, so it'll contain that hydrogen. They're made to leak before burst, so one of the tests they do is shooting them with a gun and puts a hole in it, and they have to hold together and just leak out rather than rupture the whole tank. If they're engulfed in a fire, there's a relief device that's temperature activated, so it'll open a valve and just dump it out at a safe rate before it can burn the walls of the tank to rupture. And here's the incident I was talking about where a semi rear-ended a natural gas vehicle. The tank is in there somewhere, but it kept the car from crumpling into the driver. And the investigator actually stated that the CNG tank probably saved the driver's life. So yeah, that's leading to the NREL Safety Codes and Standards program, which Carl is the head of here. So at NREL, we do lots of evaluations of safety in hydrogen. So we have our sensor laboratory. That's where I started out here. So we test the sensors that are going to be used in hydrogen, both in the safety sensors above the dispensers, the sensors that can be used on board vehicle, anything like that. There's a lot of different aspects to the safety codes and standards work that's being done here, and it all feeds into the safety codes and standards that are being put out there today that involve hydrogen. So now we're getting into the big question that everyone asks. So you have a battery that you can store it on a battery. So why would you use fuel cells? So fuel cells and batteries are the only two viable options for zero carbon emissions transportation. There's been a little bit of looking into nuclear, but I don't think anyone likes that idea anymore. But so obviously Elon Musk has been an opponent of fuel cells with his Tesla out there, and his argument is battery storage is more efficient. You don't have those efficiency losses. So why would you ever want to do fuel cells? So I took this off of Tesla's page. So this is their supercharger information. So it takes about 30 minutes to charge to 170 miles of range. 75 minutes to charge to 100% at their superchargers. So if you think about it, you could go 2.5 hours of a drive maybe if you're doing a road trip, and then you have to stop for half an hour. So it's quite a bit different than you would drive a road trip today. Some other downsides to storing on a battery is the weight of a vehicle. The Tesla is about 5,000 pounds, so it's about 1,000 pounds heavier than a fuel cell vehicle. So you have increased wear on your suspension and brakes. But overall, fuel cell vehicles are still a bit heavier than gasoline vehicles, which...
Let me just say something about the brake wear. Since on a Tesla, you're pretty much regenning whenever you slow down.
Mm-hmm.
The brakes will last for 500,000 miles.
Okay.
Anyway. So the brake wear is not a real issue.
All right.
So we can people can feel my brake rotors out there.
Okay.
Afterwards.
Sounds good. So yeah, the next step is comparing batteries to fuel cells is it's basically a change in paradigm on how you drive today versus how you're driving in electric in a battery electric society. So Elon Musk has stated that in 20 years, owning a self-driving car will be seen as a hobby. So you would basically drive a vehicle like you would have a horse today, as compared to how you used to rely on a horse for transportation. Where Toyota wants to meet the needs of their current customer base, and they really see that as their model that they're following, and they think that'll stick around. I don't know what's going to happen in the future. That's the big question to find out. Will people want to change their driving habits? It's really something we'll see in the future. Any questions? Thanks.